This is about a demo project I made with a Sipeed Go-in FPGA board. Its intention is to test how hard it would be to create an SoC out of the FPGA. And the SSB SDR has been added later as a proof of concept because well, of course, hardware is so simple that performance cannot be as good as in other receivers. Anyway, you will decide by yourself because even in this configuration, performance is not so bad. In the video, there will be some recordings of the receptions I made, and then there will be some explanation.
Delta Golf 1, Echo Bravo Oscar. Guten Abend René. Für dich 5-9 in Nordbayern und 10 Punkte für das 100-jährige Jubiläum des ersten bestätigten polnischen CSV. CSV?
Delta Whiskey Japan. Delta Whiskey Japan. 5-5, спасибо. Norway Juliet, Norway Juliet. November Juliet.
Here we have the Sipeed Tang board with the Go-in FPGA. It costs about 30 euros right now. A perf board with some analog components is connected using the PMOD connectors. You should provide an LCD display. It is about 4 euros and doesn't require any soldering. There is a flexible PCB here that should be inserted in its connector. These buttons on the Tang board are used for changing frequency and receiving mode of the SDR. These receptions were made on the 40-meter bands using a dipole. Transmitters were using the WSPR protocol. Have a look at this transmitter in the middle of the ocean. She's an icebreaker on a scientific mission to Antarctica. Her route from England tracked by the WSPR network. A full view of the analog parts that are needed to interface the RF signal to the FPGA board. We have the antenna here. We have a low pass filter, an amplifier about 10 dB of gain. This is the ADC components. These parts are not used right now. It is an integrator for a PWM audio signal, but now I'm using a DAC which is inside of the FPGA board. A close-up of the low-pass filter. Cutoff frequency is about 8 MHz. Capacitance is not the same on the input and on the output. It is not symmetrical because I would like to have some voltage gain. The amplifier uses 2 bipolar transistors. Most of these parts could be substituted by a single MMIC. Topology is the same. I just calculated the different values for the resistors in order to have a higher input impedance like for a voltage gain I was talking about before. This diagram shows the internal of the system on chip. Everything is managed by Litex. Litex is a framework that provides several peripherals and CPUs to choose from. Then it is possible to add your own peripherals and also encrypted components from the FPGA supplier or from third parties. Its output is a giant, several thousand lines long Verilog file. Then it invokes an external synthesize and place and route tools that eventually generates the bitstream file. build process is quite long. Anyway, a general advice would be to leave free a good portion of the FPGA resources to make life easier for the place and route tool. We have a VEX RiscV CPU. Since this FPGA is not so big, only a minimal configuration is used. But VEX RiscV can scale to CPUs with MMU, and it is capable of running Linux. The Sipeed board can do this. It is not extremely useful since almost all resources are taken and speed is so. Litex peripherals are quite powerful, like this SD card interface. It will contain the binary executable for the RiscV processor. Then we have an Ethernet interface here. It is used for communicating with the SoC through a bus called Etherbone. So you write a Python script or a C program, and it can read and write the internal registers of the SoC, and it is very useful for debugging or for controlling of the SoC from an external PC. And we have also other components like HDMI and also USB, but I didn't use it right now. And so the SoC incorporates also some peripherals we wrote in Verilog. There is the SDR here, the audio DAC, and the LCD interface. The receiver uses some encrypted IP from Gowin, like the DDS. This can be included like any other Verilog file, so it's quite easy and it poses no trouble at all. This is the SDR. We have the single bit ADC that feeds a 48 MHz bit stream to two mixers. The mixers are fed by two 90 degrees shifted signals, and their outputs are the baseband I and Q signals. Then, after decimation by the CIC filters, we have a 55 taps Hilbert filter for an additional 90 degrees shift. This part of the drawing represents a switch for USB or LSB reception. In one case, it shifts add to 180 degrees, 90 plus 90 here. So the two branches, when added, give a null output. When the signal paths are crossed, shifting the two branches is the same, and the signals will add. This is what happens for USB and for LSB. When the signal to be received is at a higher frequency than the local oscillator, I leads Q by 90 degrees, and the opposite happens when the local oscillator is higher than the input signal. The Hilbert filter is just an FIR filter. The coefficients are symmetric and 1 out of 2 is 0. It could be possible to have a pipeline where all of the sections work in parallel, but in this case there is no particular need for speed since the filter is placed after decimation. We don't have a lot of space, so we have only one MAC and execute it sequentially. It is 54 times slower than it could be, but it doesn't matter in this case. It's easy to configure Litex once you know how. In this file, we set the input and output pins, we give them a name and their hardware properties. In another file we add our Verilog code. It's easy to have different peripherals for the same function and select one or the other by commenting them out. so you can compare performance or have a smaller SoC during development by including only the minimum that is required for the test. These are some of the command line options used to include peripherals provided by Litex. Here at the top there's the command line that invokes Litex. We have the peripherals we talked about with some parameters like address, and these are the messages, start of the messages that are generated during the build phase. This is a C-include file generated by Litex. It defines some constants which can be used to access the command and status registers through Etherbone. It also provides the prototypes for the functions ready to be called. All of this is generated by Litex. The same thing can be done in Python on an external host. It is great for debugging. Here I was testing the NCO. CSRs can be accessed by the RiscV MCU in this way. Just include the .h file with the defines and cross-compile, linking a library supplied by Litex. Here we have some C code for the LVGL LCD display. Only a few widgets have been used. It worked as it should and it is quite easy to use. There is a background image resembling a radio panel, a label widget for the frequency, a scrolling label for some information like receiving mode, tuning step and so on. Of course, a scrolling text is a bad design choice, but I was interested in testing it. Then there is a bar for signal level. One thing to be aware, I had to define this constant table, copying it from the x86 libgcc code. It seems that the RiscV version doesn't have it. It could be possible to use a higher resolution ADC. There are a lot of boards with a 12, 14 or 16-bit ADC and better FPGA, but we want something cheap, and for about 10 euros it will be possible to have a receiver more or less on par with some other QSD radios. So thank you for your attention. There are a lot of details that couldn't be covered. If you have any question, please ask. See you later. Bye bye.